now I would like to introduce Carl Williams, who will be doing a little presentation with the CEO of Emesent, Dr. Stefan. I hope I pronounced that correctly, but I'll leave that up to Carl. Carl, are you there and ready to go? I should have first introduced Carl. Carl writes cutting-edge articles on subjects ranging from climate change to quantum computing and artificial intelligence and nanotechnology. So he is eminently suited for this. He's published work on for Nature and Royal Institution of Australia, the Australian National Data Services. He also writes independent, industry-leading content about global mining and mineral exploration industry for the Northern Miner website and newspaper, and specializes in covering technology development in the sector. Previously, Carl helped organizations manage the risk and opportunities from climate change, assisting governments and businesses in Europe, North America, India, and Australasia. So we're very pleased to have Carl here, and I will let you take it away.
Great, wonderful, Robert. Thanks for this introduction. I think we've got a fascinating discussion coming up with Stefan here. But before we sort of jump into that, maybe just give you a little bit of background about what we're talking about today. We're talking about everything drones, not the drones you see flying around above your head, taking stupid pictures of people having an ice cream out in the park of a summer day. We're talking about drones that actually operate in underground mining conditions. So why use drones? Well, they certainly provide a lot of efficiency to the mine sites, particularly in this case, underground mine site. And they provide comprehensive data of the site conditions in a very short time, often in real time as well. And they also support better coordination among the teams on-site and remotely, offering dynamic oversight of all operations. And as we become more and more connected through the cloud and some of the discussions we had earlier on, this is just going to become more and more a stronger, more powerful tool. Specifically, drones are really used in the mining environment where it's difficult, traditionally difficult to get surveying equipment there. This is particularly important for health and safety, eliminates hazardous environments where we would typically put employees into possibly dangerous zones and are navigating around the site. So all this helps foster a more inclusive environment, as well as making it safer, and provides this without disrupting operations. So it's a real privilege we have here today. We have Stefan, and again, apologies if I've mangled your surname there, Stefan. But we've had the Canadian pronunciation, now there's the Welsh pronunciation of it. So I hope that's not too long. Welcome, and I understand you're joining us from the silly o'clock in the morning in Brisbane.
Yes, morning, Carl. Hey, afternoon to everybody else in that part of the world. But yeah, no, it's a pleasure to be here, and I'm looking forward to having a discussion.
Wonderful. Thanks. And again, many thanks for joining us, Stefan. Stefan's a CEO and co-founder of Emesent, a world leader in drone autonomy, LiDAR mapping, data analytics, and particularly how, we're going to particularly talk about how his technology, we're going to focus on a thing called Hovermap, which has been commercialized by Emesent, and how that's going to assist, or is assisting, mining companies with underground operations. Just a little bit of background on Stefan. He's got the chops for this one, definitely. He's got a background in R&D, over 20 years of working in drone technology. In fact, his doctorate is in computer science and robotics from the University of Southern California. He then spent about 13 years at CSIRO, an organization I know extremely well, do some fantastic work across the scientific spectrum, where he continued his work on vision and LiDAR-based perception and navigation for drones. He's led the development and the commercialization of Hovermap, which is originally, if I got that right, Stefan, developed as a concept within CSIRO. Hovermap's a smart mobile scanning unit that combines advanced collision avoidance and autonomous flight technologies to map hazardous and GPS-denied environments, including underground mining operations. So again, Stefan, welcome to the final session here, but hopefully not the everybody's still tuned in and keeping their eyes and ears open for what's going to happen next. So as we say, a picture paints 1,000 words. So I think you're going to launch into a presentation now, which gives us the participants a much better idea of what the Hovermap technology, how it actually operates, what it can actually do, and then we will come back to the presentation. So before we dive a little deeper, and I apologies for the pun there, Stefan's going to launch into a presentation.
Great, thanks, Carl. Yeah, no, you've summed it up very well, and probably not much left for me to say. So it's a great intro. Thanks so much. I have shared a screen. Hopefully that's coming through. Let me know if that's visible on your side.
Looks good, Stefan.
Great. Yeah, so I mean, what I do today is talk about the use of autonomous systems, including drones, in the underground space, and how those can help, become an enabler for the autonomous mine of the future, specifically around how they can use to do digitization. So that's sort of mapping the survey work and also deriving insights from that 3D data that's captured. I mean, yeah, robots and autonomous systems are certainly being widely used in many industries, and the common phrase of robots to the rescue, because these systems are well suited to going into places where you wouldn't want to send a human doing the dull, dangerous, and dirty jobs, and obviously have a lot of value in doing that. So it does make sense to use them in challenging environments, but in an underground mine, I mean, it's pretty much as extreme in terms of challenging as it gets. And some additional challenges that are presented in this space that you don't typically find in sort of above ground applications. Obviously, there's no GPS, and drones typically do rely on GPS for navigation when you're operating in above ground. So using underground is definitely a challenge. Often you can't rely on having constant communication with the drone. And again, above ground you can rely on a radio control link to operate the drone. Underground, that's not the case at all. There's often no maps underground, or no prior maps that you can use to sort of reference off. And also these areas are very hard to access. So a lot of challenges for humans, but they're also the same challenge for robots and autonomous systems, including drones. So what we've done is come up with a solution to try and overcome those problems. And this is the Hovermap payload, which you've alluded to. So it's basically it's a LiDAR-based device, which mounts to a drone. And we use the LiDAR in real time. We capture that data, processes using an onboard computer, and use the LiDAR data to figure out how the drone is moving through the environment with the SLAM algorithm. So that kind of replaces the GPS requirements. And then we also build a map in real time using that data to figure out where the obstacles are and obviously where the safe areas are to fly and operate. So using that combination, it allows autonomous systems like drones to navigate without GPS, avoiding collisions, and at the same time capturing all that data on board to then produce sort of really detailed 3D point clouds. So I'll just play through a video which shows the system in operation. So on the left, you'll see the drone flying into a slope with Hovermap mounted underneath. So Hovermap ties into the drone's flight control system and basically takes over and provides that full level of autonomy. And the way it's operated is, well, there's two modes, but the way it's been shown to operate here is you have the operator has a tablet, and you can see that on the left-hand side. And in real time, we stream a live point cloud from the drone to the tablet interface. And you simply tap on that tablet, set a waypoint to task the drone and direct it where to go. And that waypoint can be set way beyond the current extent of the mapped area. And it will then self-navigate. So it's similar to self-driving car, but on a drone, it self-navigates, avoiding obstacles along the way, keeping itself safe. Always monitoring its battery health as well. So if it's getting low on battery, it knows how much power it needs to return back to the start point, and it will abandon the flight and return back to base safely. Monitoring things like dust. If the dust gets too thick, it will abandon the flight and come back home. And if it does lose connection from the operator, that's not an issue at all. It will continue flying, capturing that data. And then when the sort of it reached its last waypoint mission, it will return back to base. What you're seeing now is some of the data that's captured from the system. So this is a slope that's been mapped. And this would typically take a couple of minutes to fly in and out of a slope like this. And you can see it's kind of an idea of the level of detail that can be captured without any shadowing, and obviously without putting anybody at harm, because the system is flowing from a safe location. And yeah, just to stress that, I mean, this is a section through another slope which was mapped, and you can see the flight path taken. So the operators are standing way back from the brow to operate the system, flying in beyond line of sight. And because it flies into the void and flies around with sort of omnidirectional scanning capability, it captures everything without any shadowing. So obviously many advantage for that if you're trying to do sort of volume estimates or overbreak, underbreak in the scope. So once you have the data, yeah, one of the use cases is to do that kind of analysis. So that's an example where we're combining or comparing the slope design to the actual scan, and you can identify areas of overbreak and underbreak. So that's from sort of volumetric side of things, but Geotech's actually really excited to capture this data as well, because it now allows them to do structure mapping inside slopes, and that can be used to optimize and improve blast design for future blasts to minimize overbreak and underbreak. And something else that we're seeing recently as well is quite interesting, is that the LiDAR data is basically infrared light at a certain wavelength. So although you don't get true color from LiDAR data, you do get intensity values. And you can see here as an example where you can actually trace out geology from the intensity values in that LiDAR data, which is again another new use case, being able to do this inside a stope. The talk is about autonomous systems, but in some cases you can access areas on foot. So I mean, Hovermap has been designed to be pretty flexible, used on a drone or on something like the Boston Dynamics Spot Mini, which I'll show in a minute. But it can be taken off and hand carried on a backpack or lowered down a shaft using a protective cage. And this versatility, excuse me, means it can be used in almost any part of the mine, both underground and above ground, to digitize almost the entire mine. And talking of Spot Mini, I'm sure many of you would have seen SWAT in action in various other applications, but it's definitely well suited to underground mining as well. So this is an example where, with our partners UAS Inc. Based in Sudbury, just trialed in Kid Creek's mine. And again, another way of carrying a scanner like Hovermap to get into areas to scan them and inspect them. Drones not always the most suitable solution to get into these areas. There are benefits to having sort of ground vehicles as well. And then on the drone side, there's places that you could never send a ground robot, for example, down an ore shaft, an ore pass, sorry. So this is an example where we've flown down an ore pass that was experiencing a bit of overbreak, and again that level of detail allows you to determine how bad the overbreak might be, or if there's blockage. Or alternatively, if it's not suitable for flying, for example, if the grizzly's in the way, this is a scan done by dropping Hovermap down in that protective cage and just scanning from a cable, and again using that to do structure mapping inside an environment like this. Another example where it was lowered down a 600 or 500 meter long raised bore, which was having significant overbreak near the bottom. And one of the key uses of having the ability to scan areas like this and do it in a routine way is that you can compare the scans over time and do change detection. So this is the bottom end of that same shaft, and you can see it was scanned a couple of times, and this is comparing two scans almost 12 months apart, and color coding by change. And again, this allows you to see where things have changed and get an idea of where things could change in the future. So that's for shafts, but the same applies for convergence monitoring as well. So if mapping drifts or drives and comparing the data over time, you can get an idea of convergence in these drives. Many other use cases. Another great one we see is getting into draw points to inspect them, particularly in a block cave environment. If you're looking for a hang up, you can get in there, scan and identify what's causing the hang up, but also take other key sort of measurements of the draw points, like the roll angle and making sure the bun's in the right position, etc. And also from the LiDAR data can be fed through certain tools to derive particle size distribution as well, which is very useful. Fragmentation size analysis. And then one other great use case, I think, for autonomous systems underground is when things go wrong, which does obviously happen. So this is a case in Sweden when they had a seismic event at the LKAB's Kiruna mine, and obviously, a very challenging situation. You wouldn't want to send people in there straight after an incident like this, and having sort of shut down, having to close down operation is obviously very costly. So they were able to use Hovermap to fly into these areas and determine just how bad the the fall of ground was, and that allowed them to get back in sooner and safer to rehabilitate those areas and resume production. It was also, Hovermap's also recently used in the incident at Wale's Totten mine. Within a couple of hours after the incident, they had the system on site and they were scanning and assessing the condition of the shaft, and it's been used routinely since the incident just to keep an eye on the condition of that environment as well. And then lastly, I thought I'd show something pretty cool. So Kidd Creek have been using Hovermap for a while, and they've got great communication infrastructure as underground. So we did a proof of concept where I actually dialed in from my office in Brisbane, just using standard tools like Zoom, and logged into a laptop underground, which is on their Wi-Fi network, and then from there connected into the drone, and was able to control from my office in Brisbane and command takeoff. Here you can see I'm using the tablet interface, which usually runs on a tablet. I was just running on a laptop, so I could control the laptop, set a waypoint, command a takeoff, and start operating the drone remotely. And the reason why this is possible is because of the level of autonomy. So if you were relying on a low latency link where you were trying to react in real time to what the drone was doing, it would never be possible. But because the system's autonomous and it's looking after itself, all I was doing is giving it very high level commands with those waypoints. And obviously we had the Zoom session running, so I could watch a bit of video and see what it was doing. But that wasn't really necessary. I was getting the live stream map coming back to me in Brisbane, and that's all I needed. So I could operate this drone remotely from a different continent, even though it was underground in a mine. So that was a world first, and pretty exciting to be able to demonstrate sort of transcontinental autonomous underground drone flights using that level of autonomy. So yeah, no, I think that's just to sum up. I just wanted to sort of highlight some of the benefits of being able to do this in an underground environment. I mean, obviously a key one is being able to get better data in areas that you wouldn't otherwise be able to capture, and that drives new insights. And also this does enable sort of selective extraction and precision mining, so you have a better idea of the ore body as well. Being able to capture that data more efficiently means you can do it more regularly, and that means you can monitor those changes over time. And capturing the data in a repeatable way means you're always getting the same cut of data, so the same point density, the same level of detail. So if you are using machine learning algorithms trained to detect things in the data, it really helps to have repeated data, and that's provided through autonomy. And yeah, I mean, the vision of the future is to have these systems always on, ready to go, to be remotely operated or do routine monitoring tasks. And also it reduces the level of skill that's required for the data capture. So your geotechs or your surveyors can focus more on working with the data, and we have others that are going out and actually capturing the data. Safety is an obvious one. You're not putting people in harm's way, but also because you've got better understanding of the underground conditions, you can ensure that it's a safer environment to work with. So overall, yeah, we certainly believe that this type of technology is going to be a key enabler for the digital mine of the future, and we're always interested and excited to hear about new use cases and how this can change operations underground. So I'll leave it at that, and yeah, looking forward to getting on to some discussion points.
Fantastic, thanks, Stefan. What a excellent presentation there. I would encourage anybody as well to pop onto the Emesent website as well. There's some fantastic other case studies, lots of videos, gives you a really great feel for how these drone technologies are going to significantly add to the safety as well as the efficiency of mining operations. Stefan, maybe coming back to something that you touched on more there, talking about using the drones in anger, so to speak. Maybe that might be the wrong terminology when it comes to drones, but what if you maybe, I understand that you've been working with Glencoe at the Kidd Creek mining site in Ontario. What if you could just maybe talk a little bit about what you've been doing with them, how they've used the technology, and maybe elaborate a little bit more on what you see some of the key business benefits of companies employing these drones for their underground operations.
Yeah, I mean, sure. I mean, I think the general benefits that I've kind of covered already is the safety aspects, capturing data in places that you wouldn't otherwise being able to capture in a more efficient and safer way. And that certainly applies to Kid Creek. I mean, obviously it's a quite a unique operation with the depths that they're going to. It means they have pretty extreme conditions in terms of seismic activity and convergence, etc. So for them, they were previously, struggling to monitor those conditions, and it's critical for them to make sure that they're doing adequate ground support. So it's more than 2 years ago they first trialed Hovermap again through our partners. UAS Inc. went out and scanned, and from the first time, the first stope they flew into, I think they were pretty amazed with the data that they were able to capture. So it didn't take long until for them to come on board as a customer. And they are routinely using it every day now to scan their stopes and monitor their drives for convergence. So yeah, obviously deriving a lot of value from the system. And like I said, it's a pretty extreme mine. I think it's the closest you can get to the center of the Earth. And with a couple of world records in terms of flying Hovermap at the deepest location and doing that remote operation. So yeah, they're very great partner to work with and very enthusiastic about the technology and how it's been helping them.
Excellent. Thanks, Stefan. So I gather it goes down over 3 kilometers or thereabouts, the mine there. So
yeah.
No,
obviously we're not the drone has never flown from surface down to the bottom. It's carried down and then remotely operated or flown from there. But yeah, it's a pretty extreme mine.
Absolutely. Now we've got some questions coming in from the audience, which aren't a surprise, but I'd like to just maybe touch on a few points just before we sort of launch into the questions, which are really interesting. I think there's some challenging questions there as well for you, so be prepared. But I'd like to talk a little bit about what kind of investment or resources do companies need then, should they say work with yourselves?
In many cases, it's kind of replacing or augmenting a standard CMS, scanner. So, similar to investment from a CMS scanner perspective. Other, sort of resources and requirements, and most surveyors these days are quite sort of comfortable using drones for above ground flights. So getting a surveying team that's used to using drones up to speed usually doesn't take much. And in many cases, we train customers that have never used a drone before. So people that have usually been operating LHDs or other machinery underground, within a couple of days, we've trained them up and they're operating the system, flying into stopes. So obviously there is there's some training involved, and again that's provided by us or through our partners like UAS Inc. in Sudbury. So yeah, I think hopefully that covers the question.
Thanks, Stefan. And Stefan, maybe one thing I am curious about. Obviously, we're specifically talking about an underground mining operation that doesn't have GPS signals down there. Without going into the technical details, I'm sure we could chat for hours on the technical details, but it's using LiDAR, I understand, as a way of navigating, so it's a GPS substitute. I wonder if you could just give a little explanation, a sort of non-technical explanation, if you will, of how does that actually navigate around there? So it's kind of flying, if you will, blind, so to speak, without the GPS.
Yeah, well, it can't see the GPS, so it's blind to GPS, but it can certainly see everything else around it, because the LiDAR device is actually spraying out 300,000 points per second. And each of those LiDAR pulses is giving a range measurement just to know how far things are away. But the challenge is that's in the local coordinate frame, which is centered in the LiDAR device. So what the SLAM algorithm does is take individual snapshots of LiDAR data. So it's like, imagine a small map at a time, and it compares those two individual maps or scans and tries to identify unique features that it can recognize time and time again in those scans as it's moving. And by monitoring how those unique features are moving in its field of view, or in its reference frame, it can figure out how it's moving relative to them. It's a bit of a chicken and egg problem, because with mapping, if you don't know where you are, you can't build a map. And if you can't build a map, you can't figure out where you are. So SLAM, which stands for simultaneous localization and mapping, solves that chicken and egg problem in an iterative way. And that's kind of, I don't know if that's a great way of explaining it, but it's kind of doing, I suppose, triangulation and constellation matching off those features that it's seeing again and again to figure out how it's moving relative to them. I mean, one of the, I suppose the thing to understand is, that the data that's produced is in a local reference frame. So, when you take off, that's your 0, 0 coordinate. So usually there is a post capture step to georeference that data into the mine coordinate frame or mine grid. Many standard workflows to do that now. Again, with the LiDAR intensity values, you can see any markup that you've made on the wall or survey targets. So typically you'd survey in some targets, you'd be able to find those in the scan, and that helps to georeference the point cloud into the mine grid.
Excellent, thank you. No, that's clear. I've had many people ask me how exactly does something navigate underground without GPS, and now I've got the answer. Thank you. I'm going to jump into some of the questions that we've got coming in from the audience, because some really interesting ones here. First one I'm going to put is, how your autonomous solution compares with other high-end solutions in the market? Any thoughts, any comments on your competition, so to speak, or I think they might be referring to a sort of non-drone based technology, but maybe any comments around the question?
I mean, in the non-drone based, yeah, I mean, one of the typical tools used is a CMS scanner, and obviously been used for a long time and produces great results. But the challenges faced there are the access to the stope. You have to once you've pushed it out on a boom, you've got to wait for it to stop moving, do the scan. So yeah, access is a challenge, and there's often shadowing in a CMS scan because it's only scanning from one perspective. In terms of other drone solutions on the market, I mean, there really aren't many, because for the underground space, because it is it's a very difficult problem to solve. Obviously, we've shown that it's possible, and we were the world first to do autonomous drone flight underground, and others have followed. And there are other options on the market now, and encourage anybody to have a look around and see what options there are out there, and see what is best suited to their operations.
Excellent, thank you. Another question coming in from the audience as well. As far as your drone solution is concerned, or maybe drone solutions in general, you may want to comment on, are they insurable?
Yes, yeah. I mean, it's a piece of equipment that's used underground. So our customers do typically insure them, just like they would any other piece of equipment for use in those conditions.
Sure, thanks. Right, I'm going to read this one verbatim. Does the map restrict the operator from drive the drone into the underground walls, or the map perimeter defines the area of drive?
I think I understand the question. So the map data is used in real time on the drone to keep the drone safe. So there's two ways of operating the drone. One is through the tablet interface, where you set a waypoint, and even if you set that waypoint in the middle of the rock face, the Hovermap or the drone would never fly there. It would always keep itself safe. The other mode is, if you can see the drone, you can still use the traditional radio controls on the joystick, and Hovermap basically forms like a virtual bubble around the drone. So no matter what you do, it won't let you get too close to anything. So that mode is still very useful. I mean, if you can see the drone and you want to just sort of do some careful maneuvering into an area where you can see it line of sight, then that autonomy mode just keeps the drone safe and also keeps it stable. So if you do take your hands off the controls, it will just maintain a stable hover without having that capability. Like if in a traditional drone, if you lose GPS and you're not actively controlling it, will just drift, and obviously it doesn't have collision avoidance, so bad things could happen. But yeah, with Hovermap, it is doing that 2-in-1. Just checking the question again. I think that's answered the question, but
yeah, I know. I think that definitely has. Thanks, Stefan. Stefan, this is an interesting one. In terms of the capacity of the drones, someone's asked, do you think, in the context of the heat capacity or the heat that it generates, or is able to absorb, do you think it could help mining companies mine deeper?
So I think the question is around, can the drones withstand higher temperatures than other equipment? If that's the question, obviously there is, I mean, obviously there is a limitation for any sort of electrical equipment. It has maximum temperature ranges. You know, the drone, and again, to just mention that the drones we use are off the shelf. We're not building the drones. Our focus is on the whole map payload. So currently they can withstand typical environmental conditions in underground, but there are extremes, especially if you lose ventilation in a deep mine. Obviously the temperature can jump up quickly. So but having said that, if the focus, I mean, looking in the future, if the focus was to try and solve that problem of mining deeper through autonomous systems, then absolutely. I mean, you'd build solutions which can withstand higher temperatures and you know, operate in those sort of in a routine way, which obviously is much more comfortable than having a person down there, and also reduces the need for ventilation. So, and again, that's a general theme of, you know, the benefits of using autonomous systems in mining and sort of heading towards zero entry mining, is that you can, you know, machines are happy to operate in environments where, you know, very uncomfortable or unsafe for humans to operate.
We've got another question I'd like to ask from the audience, but before I do, I'd like to one of my own, if I will. Where would you see the landscape now going for drone technology in the mining industry? I wonder if you could maybe just future cast, if you will, and put your fingers on, and maybe put your commercial hat on as well, and think where those markets are going to be. Where do you think that technology is going, and where do you think it's going to be most useful for the mining industry? And I'm thinking specifically about those with underground mining operations, but maybe you want to talk about the mining industry in general as well.
Yeah, I mean, specifically for underground, like I said earlier, our vision of the future, and to me, it's kind of inevitable that it's going to head this way, is that these systems will be an integral part of the underground environment, both drones and other autonomous systems, but they'll be permanently based and deployed underground and launched remotely as needed to do routine monitoring and inspection. But then obviously, if there's been an incident, having that capability ready to go underground to go and do inspections, even things like, you know, post blast, after blasting, send out the drone with a gas meter, measure or, you know, check the conditions, and even if that means you can get you know, staff back in underground half an hour sooner on each shift. I mean, that's obviously a significant productivity increase there as well. So yeah, I mean, to answer your question, I think that drones and other autonomous systems are going to be a critical part of mining in the future for routine operations, and specifically valuable when there has been an incident to help out, digitizing, capturing data, feeding that all through back to you know, a centralized data management system, which accumulates all that data, runs analytics on that to derive insights, and tries to speed up that loop from data capture all the way through to insights. And, you know, that's a key part of our roadmap and what we're building as well, is to do things with the data, because having all these systems deployed capturing terabytes of data is no use unless you can efficiently derive insights from the data as well.
Yeah, absolutely. And in fact, I think that's a neat segue into one of the other questions that's come from the audience as well, about that rate of data acquisition or compared with the data processing time. I wonder if you could maybe talk to that for a moment as well, in terms of this obviously collects a huge amount of data.
I mean, that's why I mentioned it. There can be a lot of data. The raw data is around 2 gigabytes every 5 minutes in the underground environment. There's a post-processing step, which then converts that into a point cloud in a standard format, which can go into, so we've partnered up with all the major sort of software vendors, Maptech and Deswick, and Micromine and Datamine. So we're compatible with all of those systems. In our step, you can choose the level of detail you want to export from our system. So, if you want to do just rough volume calculations for a stope, you decimate the data on our side, and then it exports at a point every 10 or 20 centimeters, which is very lightweight and efficient to get into those platforms. If you need more detail to do structure mapping for geotech applications, then obviously you'd export at a higher density. So you can vary it's better to capture more than you think you might need, because there are going to be future applications, and as we develop analytics capabilities, you might want to look back at data that you captured a year ago, and now you've got new ways of deriving insights from that data. The change detection I showed in that shaft is a great example. capture the first scan, and you know, a year later you want to compare it in detail to a second scan. Processing time from our system is about 1-to-1. So if you fly or capture for 10 minutes, you'll process for 10 minutes to produce the point cloud. And then there's typically that workflow to do the georeferencing, which can take a couple of minutes depending on, you know, the tools that are used.
Wonderful. Thanks, Stefan. Stefan, I've been given the note that we've got just one more question left. And it's something that I'm particularly interested in. Is we're talking about an environment that's GPS denied. So you're using the LiDAR there as a way of getting around that, if you will, and to be able to direct you. But you're collecting all this data. Now, is that held within the platform on the drone? I was thinking more of like edge computing and how that might be able to support you. Is there something in that, or am I connecting two technologies that maybe shouldn't be connected?
No, that's certainly the case. I mean, right now, what we're doing is we're processing that data in real time to enable the flight autonomy, and we're streaming a low resolution of that to the tablet, so you can actually in real time check the coverage and make sure that you've mapped the area that you need to, but at a sort of a lower resolution. But all the data is still stored in sort of full resolution on the device. Then you transfer that to a laptop and reprocess with that 1-to-1 ratio processing time to produce the point clouds. But certainly what we're doing now is enabling that sort of processing on the device as well. So, you know, soon you'll be able to just pull off the point cloud from the device, and also doing analytics on the device as well. So I mean, other ways the Hovermap is being used is for monitoring as well. So there's an application in underground coal where, you know, we'll be using the system to monitor areas and run analytics in real time on the device to detect certain things. And like you said, edge processing. And then all you're doing is you know, sending an alert or outputting a very small piece of the data that's needed in the next part of the workflow, instead of trying to transmit the full set of raw data.
Fantastic. Well, Stefan, it's fascinating. Thank you so much for taking the time to join us today and to talk about Hovermap. And I think for those who have tuned into us, if you wanted more information, I think your website details may be provided post symposium. But again, Stefan, many thanks indeed, and please pass my best on to Brisbane and all your colleagues there as well.
Will do. Thanks so much, Carl. It's been a pleasure. Thank you.